Imagine you step onto a spacecraft, the door seals behind you, the engines ignite, and in a matter of seconds, not hours, not days, you are moving at 99.9% the speed of light, 299,792 kilometers, every single second. Now here is the part that every physicist, every textbook, every Nobel laureate agrees on, and yet almost no human being walking the earth right now truly grasps. You would age differently than everyone you left behind. Not metaphorically, not poetically. Physically, biologically, atomically, your body would tick through time at a different rate than theirs. And by the time you returned home, maybe after what felt to you like just a few years, the people you loved could be dead. Their grandchildren could be old. Entire civilizations could have risen and fallen. And here is the mind-bending part. You would not feel a thing. No weird sensation, no alarm going off, no flashing light warning you that time itself is warping around your vessel. You would simply sit there, drink your coffee, watch a movie, maybe take a nap. And the universe would quietly, invisibly, irreversibly rewrite your future. This is not science fiction. This is Einstein's special theory of relativity, published in 1905. And it has been proven, experimentally, mathematically, repeatedly, to be true. And today we are going to go so much deeper than that airplane experiment. We are going to climb inside that spacecraft and explore every single thing that happens. To the ship, to your body, to time, to space, to mass, to energy, to the stars themselves. When you push that throttle to 99.9% the speed of light, by the end of this video, you will never look at the night sky the same way again. You will never think about time the same way. You will understand something that most humans in all of history never had the tools to comprehend. And I promise you, stay with me through all of this, because the revelations get bigger, the implications get stranger, and by the very last section, we arrive at something so profound, so personal, so connected to who you are, that it will genuinely change the way you see your own life. Before we dive in, if you are new here, hit that subscribe button right now, because we do this kind of deep, mind-expanding science every single week. And I want to know something. Drop a comment below and tell me, what country are you watching from? And what time is it where you are right now? I read every single comment, and last time we had people watching from over 80 countries simultaneously. That blows my mind more than relativity does. Let me know you are here. All right, buckle in, let's go to near light speed. Right. Before we can understand what happens at 99.9% the speed of light, we need to understand why light speed matters in the first place. And to do that, we need to travel back to 1887, to a basement in Cleveland, Ohio, where two scientists were about to accidentally discover one of the most disturbing facts in the history of physics. Albert Michelson and Edward Morley had built an extraordinarily precise instrument called an interferometer. Their goal, to detect the luminiferous ether, a medium scientists believed filled all of space and through which light traveled, the way sound travels through air. If light had a medium, they reasoned, then Earth moving through that medium should cause slight variations in the speed of light, depending on which direction you measured it. They measured again. They measured in every direction. And the result? Zero difference. None. Light moved at exactly the same speed, regardless of Earth's motion. The ether did not exist, and light had no medium at all. The scientific world was shaken to its foundations. It took 18 more years for a 26-year-old patent clerk in Bern, Switzerland, a man named Albert Einstein, to explain what Michelson and Morley had found. His answer was simple, elegant, and absolutely devastating to common sense. The speed of light in a vacuum is constant. It is 299,792,458 meters per second, and it is the same for every single observer, regardless of their motion. Think of it like this. Imagine you are standing on a train going 100 kilometers per hour, and you throw a ball forward at 50 kilometers per hour. To someone standing still on the platform, that ball is moving at 150 kilometers per hour. Simple addition. That is how velocities work for everything in our daily experience. But light. If you are on that same train, moving at 100 kilometers per hour, and you shine a flashlight forward, The light does not move at the speed of light plus 100 kilometers per hour. It moves at exactly the speed of light. Period. The person on the platform measures the same value as you do on the train. This single fact, this stubborn, maddening fact, breaks Newtonian physics entirely. And Einstein's solution to this paradox was not to fix the speed of light. It was to accept it and let everything else bend around it. Space could stretch, time could slow, mass could increase. Everything in the universe was negotiable, except that one number, 299,792,458 meters per second. So why can't we go faster than light? Because as we will discover in just a moment, the closer you get to light speed, the more energy it takes to accelerate further. And the math reveals something terrifying. To actually reach light speed, you would need infinite energy. Not a lot of energy, infinite energy, which is why 99.9% is a theoretical ceiling for any object with mass. And it already puts us in profoundly strange territory. Stay with me, because in the next section we are going to get on that ship and watch the universe itself begin to change shape around us. The stars will move, space will warp, and the first truly bizarre physical transformation will begin, something called the Lorentz factor. And it is the key to unlocking everything else in this video. All right, you are on the ship, engines at full power. You are now moving at 99.9% the speed of light, and something extraordinary is about to happen to time itself. To understand it, let us meet the mathematical hero of this entire story. The Lorentz factor, named after Dutch physicist Hendrik Lorentz, who derived it in 1904, 1 year before Einstein published his relativity paper. The Lorentz factor is represented by the Greek letter gamma, and its formula is gamma equals 1 divided by the square root of 1 minus v squared over c squared, where v is your velocity and c is the speed of light. At 99.9% the speed of light, gamma is approximately 22.4. Let that number sit for a moment, because what it means is this. For every 22.4 years that pass outside your ship, only 1 year passes inside it. You age 1 year. Earth ages 22. You take a nap. A decade passes outside. You eat breakfast. 6 months of Earth history unfold while you chew your toast. Now, let me make this concrete with a real experiment, because I know what some of you are thinking. You are thinking, great theory, but does it actually happen? Yes, it does. In the 1970s, physicists began studying subatomic particles called muons. Muons are created high in Earth's atmosphere when cosmic rays slam into air molecules, about 15 kilometers above the surface. A muon has a half-life of about 2.2 microseconds. Given the distance they have to travel and the speed they travel at, about 99.9% the speed of light, coincidentally, they should decay long before reaching the ground. The math is clear. Almost none should survive the trip, and yet we detect them in enormous numbers at ground level every second of every day. Why? Because from the muon's perspective, from inside its own relativistic frame, its internal clock is ticking slower. What is 2.2 microseconds in Earth's frame is a much shorter duration in the muon's frame. The muon ages slowly. It survives the journey. It hits the ground. And every single time we measure this, it matches Einstein's equations perfectly. Think of it like this. Imagine you have a magical watch that runs on the energy of motion. The faster you move, the slower the watch ticks. At normal walking speed, you would barely notice the difference, a billionth of a second over a lifetime. But at 99.9% the speed of light, the watch ticks so slowly it is practically frozen. And here is the crucial point. It is not just the watch. It is every atomic process in your body. Your heart beats slower. Your neurons fire slower. Your cells divide slower. You are not experiencing time slowly. You are simply experiencing less of it. From inside the ship, everything feels perfectly normal. It is the universe outside that seems to be racing. But here is where it gets philosophically dizzying. And this is the twin paradox, first described by Paul Langevin in 1911. If you leave Earth, travel at 99.9% light speed, and return, you will be younger than your twin who stayed behind. not by some trick of perception. Genuinely, biologically, physically younger. You will have lived through fewer seconds of existence. Time is not a river flowing at a constant rate everywhere in the universe. It is more like a landscape, a terrain of different tempos, with gravity and velocity warping and sculpting it in ways we are only beginning to understand. Time dilation is only the beginning, because as your ship accelerates toward 99.9% light speed, time is not the only thing that transforms. Space itself, the very fabric of the cosmos, is about to start doing something that will make your time dilation seem tame by comparison. Up next, length contraction and why the universe in front of your ship will literally compress. Here is a question. If time slows down for the traveler, how does the muon reach the ground in time? From the muon's perspective, its clock is perfectly normal. It is not experiencing slow time. So how does it cover 15 kilometers before it decays? The answer is one of the most beautiful, bizarre, and logically airtight conclusions in all of physics. From the muon's perspective, the distance itself shrinks. This is length contraction, also called Lorentz contraction, and it is the perfect mathematical twin of time dilation. While the outside observer sees the muon's clock slowing down, the muon itself sees the distance to the ground contracting. Both perspectives are consistent. Both are real. Neither is an illusion. The universe is genuinely physically different depending on your frame of reference. Let's go back to your ship, moving at 99.9% light speed. That same Lorentz factor, 22.4, applies to distances in the direction of travel. A journey that measures 22 light years from Earth's frame? From inside your ship, it measures less than 1 light year. The universe in front of you has compressed by a factor of 22.4. Now here is the part that challenges intuition even further. This contraction is not just visual. It is not like looking at a distant object that appears smaller. The distances genuinely, physically contract in the direction of motion. The atoms in your ship, the gaps between them, do not contract because they are part of your reference frame. But the space between you and your destination does. Think of it like this. Imagine the universe is a gigantic accordion, and speed is the hand that squeezes it. The faster you travel, the more the accordion compresses in front of you. The musical notes, the stars, the galaxies, get pushed closer together in the direction of travel. From outside the accordion, nothing has changed, but from inside the bellows, the music of the cosmos plays at a different scale entirely. Now here is the fascinating scientific consequence. Because space contracts and time dilates simultaneously, and because they do so by exactly the same Lorentz factor, there is a beautiful symmetry at work. This is not coincidence. This is the universe protecting something called the spacetime interval, a quantity that remains constant for all observers, regardless of their reference frame. Space and time are not separate. They are two aspects of a single four-dimensional fabric called spacetime. First formulated as a unified concept by mathematician Hermann Minkowski in 1907. Einstein later admitted that Minkowski's mathematical framing was more elegant than his own original presentation. The universe does not have space and time, it has space-time. And what you and I perceive as space or time depends entirely on how we are moving through that four-dimensional fabric. Time slows, space contracts, both by the same factor, perfectly symmetrical, perfectly logical. But here is where the physics gets truly surreal, because we have not even talked about what happens to your mass yet. And when we do, in the next section, we will discover why it is genuinely, mathematically, fundamentally impossible to reach the speed of light. Not just practically impossible, structurally impossible, baked into the geometry of the universe itself. Most people know Einstein's famous equation, E equals mc squared. They have seen it on t-shirts, posters, coffee mugs, but almost nobody knows what it actually means or how it connects to everything we have been discussing. Let me tell you the full story. When Einstein was developing special relativity in 1905, he published not one but 4 revolutionary papers that year. One of them was titled, in translation, "Does the inertia of a body depend upon its energy content?" It was only 3 pages long, and it contained, buried in its mathematics, the seed of the most important equation in human history. What Einstein showed was this. Mass and energy are not two separate things. They are two forms of the same thing. Mass is frozen energy. Energy is liberated mass, and the conversion factor between them, the rate of exchange, is the speed of light squared, which is an enormous number, roughly 90 quadrillion joules per kilogram. 1 kilogram of matter, fully converted to energy, would release the equivalent of 43 million tons of TNT. That is why nuclear weapons are so destructive. They convert only a tiny fraction of their mass to energy, and that fraction is enough to level cities. But here is where it connects to our ship at 99.9% light speed. As an object accelerates toward light speed, its relativistic mass increases. Not its rest mass, the mass that physicists today prefer to call invariant mass, but its total energy and therefore its effective mass. The resistance it presents to further acceleration increases with the Lorentz factor. At 99.9% light speed, your ship's relativistic mass is 22.4 times its rest mass. It is 22.4 times harder to accelerate than when it was sitting still. To push it even faster, to go from 99.9% to 99.99%, you need enormously more energy. And the math shows that as you approach exactly 100%, the energy required approaches infinity. Think of it like this. Imagine you're trying to run up a hill that gets steeper as you go. At first it is gentle and you make good progress, but as you climb, the hill curves upward more and more steeply. By the time you near the top, you are practically climbing a vertical wall. And the top itself, 100% light speed, is a perfectly vertical cliff face that extends infinitely upward. You can get closer and closer to it, but you can never reach it. This is not a limitation of your legs. It is a limitation of the hill's geometry. Now, here is where EMC2 becomes relevant in a new, more terrifying way. As your ship moves at 99.9% light speed, it is accumulating enormous kinetic energy. That energy is real. It has mass equivalent. If something were to suddenly stop your ship, slam it into a wall, so to speak, all of that kinetic energy would need to go somewhere. The result would be a release of energy so vast, it would dwarf nuclear explosions. Which brings us, naturally, to the most dangerous physical threat aboard your light-speed ship, the interstellar medium. Because here is what nobody tells you in the glossy space travel brochures. Space is not empty, and at 99.9% light speed, the thin veil of hydrogen atoms drifting between the stars becomes something far more deadly than any weapon we have ever built. Stay with me. The next section will show you what those atoms actually do to your ship. In everyday terms, space is a vacuum. There is essentially nothing out there. But essentially nothing is not the same as absolutely nothing. The interstellar medium, the matter that exists between star systems, contains on average about 1 hydrogen atom per cubic centimeter. 1 atom per cubic centimeter. You might be thinking, 1 atom per cubic centimeter, that is almost nothing. What possible harm could that do? At normal spaceship velocities, even the fastest spacecraft we have ever launched, like Voyager 1 at roughly 0.06% the speed of light, the answer is virtually none. The atoms are too sparse, and the ship is too slow for them to matter much. At 99.9% the speed of light, the answer changes catastrophically. Let us do the math. At 99.9% the speed of light, your ship is sweeping through space at approximately 300 million meters per second. In 1 second, it crosses 300 million cubic meters of space, and at 1 hydrogen atom per cubic centimeter, that is 300 trillion hydrogen atoms hitting your ship every single second. 300 trillion atomic collisions per second. But it gets worse as because of relativity. From your ship's reference frames, remember length contraction, those hydrogen atoms are not moving at normal speeds. They are slamming into you with relativistic energy. Each hydrogen atom, from your perspective, has kinetic energy roughly equivalent to a proton at the Large Hadron Collider in CERN, a particle accelerator, on your hull. 300 trillion times a second. Now theoretical physicists have proposed solutions. The most elegant is the electromagnetic deflector, essentially a powerful magnetic field projected far ahead of the ship that ionizes incoming hydrogen and deflects it away before it reaches the hull, the way Earth's magnetosphere deflects the solar wind. In principle, this could work. In practice, the engineering challenges are immense, but the physics allows it. There is also the question of interstellar dust, particles larger than atoms, ranging from nanometers to micrometers in size, that drift between stars in low concentrations. At 99.9% light speed, even these tiny grains become high-velocity projectiles. A grain of dust 1 micrometer across would hit with the energy of a rifle bullet. A pea-sized rock would hit with nuclear bomb energy. The ship would need to either deflect these or detect and destroy them in advance, at a range of hundreds of kilometers given the approach speeds involved. Think of it like this. Imagine you are running through a light drizzle of rain. At normal running speed, the droplets hit you gently. You feel damp, but unharmed. Now imagine running at the speed of a bullet. Those same gentle raindrops become high-velocity projectiles that could punch through steel. The rain has not changed. Your velocity has. And at 99.9% light speed, the gentle drizzle of space becomes a wall of radiation and projectiles that would destroy any ship we could build today. Yet, and this is the hopeful note, none of this violates the laws of physics. These are engineering problems, not physical impossibilities, and that distinction matters enormously, as we will explore later in this video. But first, let us leave the brutal exterior of our ship and go inside. Because what is happening inside the ship to the humans aboard is arguably even stranger. We have talked about time, space, mass, and the physical bombardment of interstellar matter. But here is a question we have not asked yet. What does it look like from inside the ship? What do you see when you look out the window at 99.9% light speed? The answer involves something called relativistic aberration and the Doppler effect, and it will produce one of the most visually spectacular and deeply strange phenomena we have discussed yet. Coming up next, close your eyes and imagine. You are sitting at the observation window of your ship. It is quiet. The engines hum. You are cruising at 99.9% the speed of light. You lean forward and look out at the universe. What do you see? Not the peaceful scattering of stars you might have imagined. Not the gentle river of the Milky Way. What you see is something that would look like it was designed by a science fiction artist having a fever dream, and yet every detail of it follows perfectly from the physics we have already discussed. The first phenomenon is called relativistic aberration. At normal speeds, light from all directions reaches your eyes from those directions. Stars ahead are in front, stars behind are behind. But at 99.9% light speed, the light from stars to the side, above, below, and behind you is bent, aberrated by your motion. The stars appear to crowd together ahead of you, as if the entire universe is being swept toward the direction of travel. At 99.9% the speed of light, almost all the visible stars in the universe would appear to be within a narrow cone of perhaps 10-15 degrees directly ahead of you. The sides and back of your view would be almost completely dark. The universe has collapsed into a bright, jeweled bullseye ahead of your ship. But that is only the beginning. The second phenomenon is the relativistic Doppler effect, the shift in light frequency due to your motion. Stars ahead of you are not just visually compressed, their light is blue-shifted. The waves of light are compressed by your approach, just as a car horn sounds higher-pitched when the car is moving toward you. Stars directly ahead that might normally shine in visible yellow or red light are shifted into the ultraviolet, then the X-ray, then the gamma-ray spectrum. They become invisible to the naked eye, but they are pouring out lethal radiation. Stars behind you, meanwhile, are red-shifted, their light stretched out into the infrared, and then the radio spectrum. They fade and disappear from visible view. The universe behind you goes dark, and the beautiful, terrible glow ahead of you brightens, not with visible light you can see safely, but with high-energy radiation that would, once again, require heavy shielding to survive. There is a third visual effect, perhaps the strangest of all, called Terrell rotation. At relativistic speeds, objects appear to rotate rather than contract. If you were to observe a cube passing you at 99.9% light speed, it would not appear flattened or compressed. It would appear rotated, as if you were seeing it from a different angle than its actual direction of travel. This is because light from different parts of the cube left at different times to reach your eye simultaneously. And this timing difference creates the illusion of rotation. The universe at 99.9% light speed is not something any human has ever seen. It is not something any camera has ever captured. But the mathematics is airtight, confirmed by particle accelerators and stellar observations, and every single effect described here would be real, verifiable, measurable. Think of it like this. Imagine standing in the center of a stadium, and instead of people sitting all around you, they all suddenly rush to one end, the end you are running toward, and crowd together in a bright, dense mass. The stadium has not physically changed, but from your moving perspective, all its occupants have compressed into a single bright corner of your vision. That is relativistic aberration. Now add the fact that all those people are screaming at frequencies you cannot normally hear, some too high, some too low, and you start to glimpse the alien sensory experience of near light speed travel. We have now fully explored what physics does to your ship and your senses at 99.9% light speed. But here is the question that philosophers and scientists have debated for over a century, and that I promised would connect personally to you. What does all of this mean for causality, for free will, for the nature of the past, present, and future? Because special relativity does not just change how we experience time, it eliminates the concept of now. And that revelation, coming up next, is the one that changes how you see your own life. I want to stop for a moment and step away from the ship, away from the equations, away from the gamma rays and the length contraction and the aberrated star fields. I want to talk to you, the person watching this right now, wherever you are in the world. Because what we have been discussing is not just a curiosity about distant hypothetical spacecraft, it is a description of the reality you are living in. Right now. This moment. Here is a concept that Einstein himself found deeply troubling late in his life, the relativity of simultaneity. When I say the word now, when I say right now you are watching this video, I am implying that there is a single universal now that we share, a present moment that exists across the cosmos, a thin slice of time called the present, with the past behind it and the future ahead. Relativity proves this does not exist. Two events that are simultaneous in your reference frame are not simultaneous in a reference frame moving relative to you. Now is not a universal truth. It is a local perspective. What is happening right now on a planet 10 light-years away is undefined. It depends on the velocity of the observer asking the question. Physicist Brian Greene, in his book, The Fabric of the Cosmos, describes what he calls the Andromeda paradox, a scenario first articulated by Roger Penrose. Two people walking past each other on a street are moving at slightly different velocities. Because of relativity, their definitions of now on the Andromeda galaxy, 2.5 million light-years away, differ by thousands of years. One person's now on Andromeda corresponds to a time when, say, an alien fleet is still deliberating whether to launch toward Earth. The other person's now corresponds to a time when that fleet has already launched and is on its way. Both are equally valid. Neither is more real. The present is not a universal fact. It is a local, velocity-dependent perspective. Now think about what this means for you. Every photograph you have ever taken is a moment that, somewhere in the universe, in some reference frame moving at some velocity relative to yours, is still now. The past is not gone. It is not destroyed. In a very real, relativistically valid sense, every moment you have ever lived is preserved in the four-dimensional geometry of space-time. Physicist Julian Barber has written about what he calls the end of time, not as a catastrophe, but as a revolution in understanding. Time, in his interpretation of physics, does not flow. There is no river of time carrying you from past to future. Instead, all moments, every instant of every life ever lived, exists simultaneously in the four-dimensional block universe that special and general relativity describe. What we perceive as the passage of time is a path through that block on our world line, not a change in the block itself. What does this mean for you personally? It means that the child you were at 5 years old is not gone. That moment is geometrically fixed in space-time. It exists. Not in memory, not in photographs, actually exists as a coordinate in four-dimensional reality. The person you will be in 10 years already exists too, in some sense as a part of the space-time geometry that has not yet intersected with your consciousness. You are not a thing moving through time. You are a four-dimensional object, a world line, extended through space-time from birth to death, all of it equally real, all of it existing simultaneously in the block universe. I am not going to tell you whether this is comforting or terrifying. That reaction is personal. But I will tell you that physicists who sit with this idea long enough, physicists like Albert Einstein, who wrote in a letter after the death of his lifelong friend Michel Besso has departed this strange world a little ahead of me. That signifies nothing. For those of us who believe in physics, the distinction between past, present, and future is only a stubbornly persistent illusion. These scientists find in it something closer to peace than despair. You are not just a creature of this moment. You are a four-dimensional being, and that makes you, in a very real sense, cosmic. Pause here for a second. If this section hit differently than the physics sections, if thinking about your own existence in a relativistic universe gave you a moment of vertigo or wonder, drop a comment below. Tell me what you felt, because this is exactly why science matters beyond the equations and experiments. It changes how we understand ourselves. And if you are not subscribed yet, do it now, because we are about to go even deeper. If there is no universal now, and if the past is as real as the present, does that mean time travel to the past is possible? Could you somehow use near light-speed travel to go back, to undo mistakes, to revisit lost moments? The answer, as far as special relativity is concerned, is an emphatic no. And the reason involves one of the most important concepts in all of physics: causality. Causality is the principle that causes precede effects, that you cannot receive a message before it is sent, that you cannot be killed before the gun fires, that the arrow of time always points from cause to effect, never backward. Special relativity and causality are deeply intertwined. The speed of light is not just a speed limit, it is the enforcement mechanism of causality. Nothing, no matter, no energy, no information can travel faster than light. And this is what prevents any form of backward causation. Here is the logical chain. If information could travel faster than light, then in some reference frames it would arrive before it was sent, because of the relativity of simultaneity. An observer, moving relative to you, would see the effect occur before the cause. Causality would be violated. The universe would be logically incoherent. Effects would precede causes. The future would influence the past. Logic itself would collapse. Einstein recognized this immediately. The speed of light is not just a physical constant. It is the boundary condition of a causally consistent universe. Break it, and you do not just go fast, you break the logical structure of reality. This is why physicists are deeply skeptical of proposals for faster-than-light travel, like the Alcubierre warp drive. Not just because of the engineering challenges, but because if such travel were possible, it would almost certainly enable closed time-like curves, paths through space-time that loop back on themselves, grandfather paradoxes, effects preceding causes, a universe where you could prevent your own birth. Stephen Hawking proposed what he called the chronology protection conjecture in 1992, essentially a hypothesis that the laws of physics conspire to prevent time travel to the past, perhaps through quantum mechanical effects that would destroy any time machine before it could be used. He called it a conjecture, supported by the evidence that we have not been invaded by hordes of tourists from the future. Think of it like this. Causality is the grammar of the universe. Without it, events could not have meaning, actions could not have consequences. The entire structure of if this, then that, which underlies not just physics, but logic, language, and consciousness itself, depends on causes preceding effects. The speed of light is not just a fact about photons. It is the universe's way of protecting its own internal consistency. It is the universe making sure its story remains coherent. We have traveled far together. Let me bring it all home. We began with a ship, a spacecraft accelerating to 99.9% the speed of light, a velocity that humanity has never achieved, but that the laws of physics do not forbid. And we asked, what actually happens? Here is what we discovered in the order we discovered it. Time slows down by a factor of 22.4. For every year you experience on the ship, 22.4 years pass on Earth. This is not metaphor. It is physical fact, confirmed by atomic clocks on airplanes, by muon survival rates, by GPS satellites that would give wrong directions if they did not correct for relativistic time dilation every single day. Space contracts, by the same factor of 22.4. A journey of 22 light-years feels like less than 1 light-year from inside the ship. The universe physically compresses in the direction of travel. Distance is not absolute. It is relative to velocity. Mass and energy explode. The ship's relativistic mass is 22.4 times its rest mass. Every ounce of acceleration requires increasingly enormous energy. Reaching light speed itself would require infinite energy, making it not just practically but fundamentally impossible for any massive object. The interstellar medium becomes lethal. Thin as space is, at 99.9% light speed, each hydrogen atom becomes a particle accelerator energy projectile. Survival requires either electromagnetic shielding or some other deflection technology. But the physics allows it. The universe transforms visually. Stars crowd into a bright disk ahead of you via relativistic aberration. Light blue shifts into deadly gamma radiation. The cosmic microwave background becomes a lethal wall of ancient energy. The universe at 99.9% light speed is alien, beautiful and lethal. There is no universal now. Simultaneity is relative. The past is permanently encoded in spacetime. The block universe encompasses all moments, past, present, future, simultaneously. Your life is a four-dimensional object in the geometry of spacetime. Causality is sacred. Nothing can travel backward in time. The speed of light is the enforcement mechanism of a causally consistent universe. But time dilation allows forward time travel. If you travel fast enough for long enough, you can leap into Earth's future. The engineering is not forbidden. Every challenge, energy requirements, radiation shielding, deceleration, is a technological problem, not a physical impossibility. A sufficiently advanced civilization could, in principle, build this ship. The cosmos is vast, silent, and possibly lonely. The Fermi paradox remains unsolved. Relativity may be part of the reason, isolating civilizations from each other across cosmic distances and time. But we have barely begun to listen. The universe will die. Accelerating expansion will eventually leave us alone in a dark, cooling cosmos. But in a block universe where all moments exist simultaneously, the end is a coordinate, not an erasure. Every moment of cosmic history is permanently real, and consciousness is magnificent. You right now are a configuration of stardust capable of understanding all of this. You are the universe knowing itself. Your life is encoded in space-time geometry, permanent and real, regardless of what anyone tells you about insignificance. Here is the final thought I want to leave you with. We live in an age where it is easy to feel small. The universe is 93 billion light-years across in the observable direction. It is 13.8 billion years old. Our planet is a pale blue dot, orbiting an ordinary star in the outer suburbs of an unremarkable galaxy, among hundreds of billions of galaxies. In the face of all that, it is easy to conclude, I do not matter. But special relativity, this beautiful, strange, experimentally confirmed description of reality, tells a different story. It tells us that space and time are not separate, absolute things. They are a unified fabric that bends and stretches and warps around mass and velocity. It tells us that the now you are experiencing is not a universal fact, but a local perspective, your personal cross-section through a four-dimensional reality that contains every moment that has ever existed. It tells us that your entire life, every second of it, is a permanent geometric structure in the space-time of the universe. You are not passing through time, you are woven into it. And the fact that you can understand this, that you can watch a video like this and build a working mental model of relativistic time dilation and block universe cosmology and the visual experience of near light speed travel, that is not a small thing. That is the universe achieving self-awareness. That is something that, as far as we know, has happened nowhere else in the observable cosmos. We are early. We are young. We are barely a century into understanding relativity, barely 60 years into the space age. We have not yet traveled at 99.9% the speed of light. We have not yet found another mind in the darkness of space. We have not yet answered the deepest questions about consciousness and time and the ultimate nature of reality. But we are asking them. That is the beginning of everything. Thank you for traveling this far with me today. If this video expanded your understanding even slightly, if there is one moment where your mind did something it has never quite done before, then we have done something worth doing. Drop a comment below. Which section hit you hardest? Which idea are you still turning over in your mind? Tell me what country you are watching from and what time it is there. I want to know how far across this small planet these ideas have traveled today. If you are not subscribed, please subscribe now. We do this every week. Deep dives into the science that matters, explained in ways that respect your intelligence and feed your wonder. Share this video with someone who needs their mind expanded. And I will see you in the next one. Because the cosmos does not stop being fascinating just because the video ends. Stay curious. For those of you who want to go deeper into the mathematics, who are not satisfied with the conceptual understanding and want to see the numbers, this extended section is for you. We are going to work through the Lorentz transformation equations step by step. The Lorentz transformation describes how to convert measurements of space and time in one inertial reference frame to measurements in another frame, moving at constant velocity relative to the first. There are 4 equations, one for each of the 4 spacetime dimensions. For simplicity, let us consider motion only in the x direction. Frame S is the stationary frame, let us say Earth. Frame S' is the moving frame, your ship moving at velocity v relative to Earth. The equations are x', gamma times x minus v times t, t', gamma times t minus v times x divided by c squared, y', a y z', z, where gamma is the Lorentz factor, 1 divided by the square root of 1 minus v squared over c squared. Let us plug in our numbers. At 99.9% the speed of light, v equals 0.999 c, so v squared over c squared equals 0.998 tau01. 1 minus that equals 0.01999. The square root of 0.0199 is approximately 0.04472, and 1 divided by 0.04472 is approximately 22.37. Our Lorentz factor of 22.4. Now let us see what this means for a specific scenario. Say a supernova happens 10 light years ahead of your ship, and it happens in Earth's frame, at time t equals 0. In Earth's frame, the event has coordinates x equals 10 light years, t equals 0. In your ship's frame moving at 0.999 c, the time of that supernova is t' equals 22.4 times 0 minus 0.999 times 10 divided by c squared, working through the light year and year units. Result, approximately negative 22.4 times 9.99 years, which is roughly negative 224 years. What does a negative time mean? In your ship's frame, that supernova happened about 224 years ago. In Earth's frame, it is happening right now. The same event, a star exploding, occurred at completely different times in different reference frames. Neither is wrong, both are real. This is the relativity of simultaneity made concrete. This is why physicists say that in special relativity, there are no preferred reference frames. The laws of physics are the same in all inertial frames. Earth's now is not more real than the ship's now. The muon's reference frame is not less valid than the laboratory's. The universe does not have a master clock. It has billions of clocks, all running at different rates depending on their motion, all equally real, all equally valid. The Lorentz transformation is not just a mathematical trick. It is a description of the actual physical structure of spacetime. When Hermann Minkowski saw these equations in 1907, he recognized their deeper meaning. They are the transformation rules for rotating in 4-dimensional spacetime, swapping some amount of space for time and vice versa, the way ordinary rotations swap x and y coordinates. Motion through space is, in a deep sense, a kind of rotation through spacetime. The faster you move through space, the more you are rotating your spacetime orientation, and the slower you move through time. we have focused entirely on special relativity, the physics of constant velocity motion. But there is a profound extension that Einstein developed between 1907 and 1915, general relativity, which extends the principles of special relativity to include acceleration and gravity. Einstein's key insight, the one he called the happiest thought of my life, was the equivalence principle. The experience of being accelerated is indistinguishable from the experience of being in a gravitational field. If you are in a windowless box accelerating upward at 9.8 meters per second squared, you feel exactly the same force as you would standing on Earth's surface. There is no experiment you can do inside the box to tell the difference. This equivalence implies something extraordinary. If acceleration affects light and time, then so must gravity. And Einstein's general relativity shows exactly how. Massive objects curve the fabric of spacetime, and this curvature is what we experience as gravity. The planets orbit the Sun not because the Sun pulls on them, but because the Sun's mass has curved spacetime such that the straightest possible path through it, a geodesic, is a curved orbit. And crucially, because massive objects curve spacetime, they also dilate time. Deep in a gravitational well, time runs slower. This is gravitational time dilation, distinct from but related to the velocity time dilation we have been discussing. This is not theoretical. The GPS satellites in orbit around Earth must correct for both types of time dilation. The satellites are moving relative to Earth's surface. Special relativistic time dilation slows their clocks by about 7 microseconds per day. But they are also farther from Earth's gravitational center than we are. General relativistic gravitational time dilation speeds their clocks up by about 45 microseconds per day. The net effect: their clocks run about 38 microseconds fast per day compared to ground clocks. Without correcting for this, GPS position errors would accumulate at about 10 kilometers per day. Every time you use Google Maps to navigate, you are implicitly relying on Einstein's relativity being correct. Near a black hole, where space-time curvature is extreme, gravitational time dilation becomes dramatic. At the event horizon of a black hole, time dilation becomes infinite. A clock at the event horizon, from a distant observer's perspective, stops. Time freezes. The infalling observer, from their own perspective, experiences nothing unusual at the event horizon. They cross it in finite proper time, but they are cut off from the external universe forever. Physicist Kip Thorne, who won the Nobel Prize in Physics in 2017 for his work on gravitational waves, has written extensively about the experience of approaching a black hole. The tidal forces, the difference in gravitational pull between your head and your feet, would stretch you into a thin strand of matter in a process scientists call magnificently spaghettification. For a stellar mass black hole, this would happen well outside the event horizon. For a supermassive black hole like the one at the center of our galaxy, 4 million solar masses, imaged indirectly in 2022 by the Event Horizon Telescope, the tidal forces at the horizon are gentle enough that you might cross it without feeling anything unusual. You would simply be inside forever. We have spent this entire video in the realm of classical special and general relativity. But there is another pillar of modern physics, quantum mechanics, and the relationship between these two frameworks is one of the deepest, most productive, and most frustrating in all of science. Special relativity and quantum mechanics were unified in 1928 by Paul Dirac, who developed the relativistic quantum wave equation for the electron, now called the Dirac equation. This was one of the most fruitful acts of theoretical physics ever performed. The Dirac equation predicted the existence of antimatter before it was discovered. When physicists solved the equation, they found it had two solutions, one for the electron and one for a particle identical to the electron, but with opposite electric charge. In 1932, Carl Anderson discovered the positron, the electron's antimatter twin, exactly as Dirac's equation had predicted. A triumph of mathematics revealing physical reality. The union of special relativity with quantum mechanics produced quantum field theory, the framework that underlies our standard model of particle physics. In quantum field theory, particles are not billiard balls, but excitations in underlying fields that permeate all of space. The electron is a ripple in the electron field. The photon is a ripple in the electromagnetic field. Higgs bosons, discovered at CERN in 2012, are ripples in the Higgs field that gives other particles their mass. But general relativity, quantum mechanics' great sister framework, has stubbornly resisted unification with quantum mechanics. Attempts to quantize gravity lead to infinities that cannot be renormalized away. The equations break down at the Planck scale: lengths of 10 to the minus 35 meters, energies of 10 to the 19th power GeV. String theory, loop quantum gravity, causal dynamical triangulations, all are attempts to resolve this incompatibility. None has yet produced a testable prediction that would distinguish it from rivals. This incompatibility is the deepest open problem in theoretical physics. It means our understanding of reality is fundamentally incomplete. We have two extraordinarily successful frameworks: general relativity, which describes the very large, and quantum mechanics, which describes the very small, and they cannot both be fully correct as currently formulated. At extreme conditions, inside black holes, at the moment of the Big Bang, both frameworks break down simultaneously, and we have no physics to replace them. Physicist Lee Smolin, in his book The Trouble with Physics, argues that this crisis is not just a technical problem, but an indication that our conceptual framework is fundamentally wrong, that the next revolution in physics will require abandoning not just our equations, but our most basic assumptions about space, time, and causality. Perhaps time is not fundamental but emergent. Perhaps space is not continuous but discrete at the Planck scale. Perhaps the block universe of relativity and the probabilistic collapse of quantum mechanics are both approximations of a deeper reality we have not yet conceived. The universe at 99.9% the speed of light is strange. The universe at the Planck scale is stranger still, and the universe that contains both, the real, actual, physical universe we inhabit, is stranger than we can currently imagine. That is not a failure. That is an invitation. Let us end where we began, with the ship. It is the year 2024. No human has ever traveled faster than about 40,000 kilometers per hour, the speed of the Apollo missions returning from the moon. The fastest object we have ever launched, the Parker Solar Probe, at its closest approach to the Sun, reaches about 690,000 kilometers per hour. That is 0.064% the speed of light. Magnificent by human standards, a rounding error compared to 99.9%. But consider how quickly we have developed. In 1903, the Wright brothers flew 120 feet in 12 seconds. 66 years later, humans walked on the moon. In 1945, we detonated the first nuclear weapon. 27 years later, we had mastered controlled nuclear fission for power generation. In 1953, Watson and Crick described the structure of DNA. 70 years later, we were editing genomes with CRISPR with surgical precision. The history of technology is a history of exponential acceleration. What takes 1,000 years in one century takes 100 years in the next and 10 years after that. The challenges we have described for relativistic travel, antimatter production, electromagnetic shielding, extreme engineering, are challenges of scale, not kind. We know how antimatter works. We know how electromagnetic fields work. We know what we need. We do not yet know how to produce it at the required scale. There is a framework for thinking about civilizational scale, developed by Soviet astrophysicist Nikolai Kardashev in 1964. The Kardashev scale classifies civilizations by their energy consumption. A type of Karnan civilization harnesses all the energy available on its home planet, roughly 10 to the 16th power watts. A Type 2 civilization harnesses the full energy output of its star, 4 times 10 to the 26th power watts. A Type 3 civilization harnesses the full energy output of its galaxy. Earth's current civilization is roughly a Type 0.73. We use about 2 times 10 to the 13th power watts. We are not yet Type 1. But physicist Michio Kaku estimates we will reach Type 1 within 100 to 200 years, assuming continued technological development. Type 2, harnessing the full sun, may be achievable within a few thousand years. And a Type 2 civilization has the energy budget to run an antimatter production facility, power electromagnetic deflectors, and achieve near-light-speed travel. A few thousand years. In the context of a 13.8 billion-year-old universe, a few thousand years is nothing. We are extraordinarily early. The technologies we have been discussing are not the fantasies of a civilization that has reached its limits. They are the ambitions of a civilization that has barely begun. And this brings me to the most personally significant conclusion of this entire exploration. You are watching this video at perhaps the most extraordinary moment in the history of our species. We live in the 1st century, when humans have understood relativistic physics well enough to work with it practically, to use it in GPS, in particle accelerators, in the equations that guide our deepest telescopes. We live in the 1st century, when we have directly detected gravitational waves, the ripples in spacetime that Einstein predicted in 1916. We live in the 1st century, when we have imaged a black hole. We are not at the end of the story. We are at the very beginning of a story that will, if we survive and grow, play out across thousands and eventually millions of years. The light-speed ship we have been discussing is not a fantasy for a civilization like ours. It is a project for a civilization a few centuries or millennia older than we are. And we are exactly the generation that is laying the conceptual foundations, understanding the physics, building the early technologies, asking the right questions, that will make it possible. Every physicist who explained special relativity to a student, every science communicator who made it accessible to a wider audience, every curious person who watched a video like this one and came away with a slightly larger understanding of the cosmos, they are part of the chain of human understanding that stretches from Einstein's 1905 papers forward to whatever species of technological civilization our descendants become. You are part of that chain. Right now, this video is part of that chain. We began with a ship at 99.9% the speed of light, and we end here, with you, sitting wherever you are in the world, having spent the last several hours expanding your understanding of the universe you inhabit. Time dilation, length contraction, the block universe, the death of the cosmos, the magnificence of consciousness, the openness of the future. None of it is separate from you. All of it is part of the same story, and that story is not over, it has barely started. Thank you for watching. I will see you in the next video. Stay curious, stay humble, keep looking up.